There's nothing surprising up to this point, okay? Now, next up, I'm going to represent the yi. Yi is pi transpose times x or x transpose times pi, okay? So I write this yi squared as this, okay? Distribute the expectation inside, and I have that. Okay, so after a lot of just basic vector matrix manipulations, I get my mean square error to be this. Can you recognize this? What is this? That's RXX. That's the autocorrelation matrix. That's the autocorrelation matrix. So that turns out to be RXX times pi transpose times pi. Okay, and we want this to be minimum. Okay. So another reminder. If I have RXX times E equal to lambda times E, then lambda is the eigenvalue of RXX, and E is the eigenvectors of RXX. Okay? I will need that. So the question becomes this. Okay? Minimizing the mean square error, which we manipulate to show that is equal to this. Okay? With respect to these constraints, we need the orthonormal constraints. Right? Those are the only constraints that we need to do. So what is the solution? What type of approach should we do? I'm looking for the magic keyword. What is the magic keyword for constraint optimizations? Lagrangian, right? We need the Lagrangian, right? So without the constraint, you just take derivative like we did before. But with the constraint, you need to introduce the lambda. Okay, the Lagrangian, and then take into account the phi. Okay, so the Lagrange multiplier technique is this. So minimize the mean square error, and you have to take into account the constraint. Okay, so that adds the second part to the equation. Okay, now I'm taking the derivative with respect to a vector. I'm taking the derivative with respect to a vectors, okay? So I need some of these basis manipulations. The derivative with respect to the vector v of u transpose times v is just u itself. The derivative with respect to the vectors v of v transpose times av is equal to 2av. Just like when you do v squared in scalar form, okay? Now, if you feel a little lost here, don't worry about it. Go back to your basic matrix vectors textbook and try to verify these step by step. Okay, since we don't have much time left. So this is what we have to do. Okay, this is eigenvectors of your set based on that RXX matrix, autocorrelation matrix. Choose the basis function as the eigenvectors, okay, and you have n of them. You have n basis functions, okay, and then send the larger eigenvalues first, because that will minimize the mean square errors. Okay, this is very important. Okay, so let's step back. Okay, if you're lost within somewhere between point 1 and point n here, don't worry about it. Okay, let's step back and take a look at this very nice equation. Okay, what it's saying is that in order to design the optimal transform, you should pick all your basis function to be eigenvectors of RXX. Okay, that's all it's trying to say. Pick your eigenvectors as the basis function. Okay, and if you pick the eigenvectors as the basis functions, the transform coefficients will turn out to be eigenvalues. Okay? Send the eigenvalues over. Okay? And you should the larger guy is obviously a lot more important than the smaller guy because of this property. Okay? The errors is a summation of all the eigenvalues that you throw away. So you should throw away the small one and send the large one. Okay? That's all there is to it. Now, in practice, we actually, I don't know if you guys know the eigenphase techniques that people at MIT use for face recognition. They actually use the same techniques. Okay, every face they compute the RXX of they compute a few large eigen values of each of the face, and they compare faces on the eigenspace. So that's called eigenphase. Okay, they only compare the first few coefficients. Okay, and if it's matched, the first few coefficients should match well. Okay, so for example, female and male. Female has a different set of eigenvalues, and male has a different set of eigenvalues. Hopefully, right? And that's how they tell male-female apart. Okay, for example. So people actually use this a lot in practice. Now, let's think about the problem that we have to face. We managed to prove a nice theorem. By the way, this problem is formally posed also in the 1950s. Okay, along with Loimax, along with entropy coding techniques. Okay, so we know this for a long time. Okay, now the next question is, can we actually use this in practice? Okay, anybody has any problem with this?
The computation is very complicated.
Right. So what happens at the encoder? That doesn't seem to be any problem, right? Computing the eigenvectors, eigenvalues. Okay, computationally expensive, but it can be manageable. Okay. Let's think about the decoder. What does the decoder need to reconstruct? It has to know what basis function being used in the encoder, right? How do you send it over?
You have to send over the basis function.
Okay, you have to send over the basis function with the signal. Is there anything wrong with that? What is the size of the basis function? Same size as your original signals, right? How many basis functions do you have? N of them, right? Okay, that wash out your compression. Okay, right? You have to send the basis function along with the filter transform coefficients, right? For the decoder to be able to decode. So that just wipe out your compression. Okay? And then each of does your basis function change?
No. Yes.
Yes, because it's dependent on the signal.
Okay.
It's dependent on the signals, right? Every signal has a different RXX. Okay? And so the decoder doesn't know. Okay? Now if we use Fourier transform, does the decoder know? Yes. The Fourier transform is fixed, right? Okay, it's E, J, omega, whatever. So the decoder knows exactly what the encoder used. So that is a problem. This is optimal, but it has no practical value whatsoever. Okay, we learned good lesson from it, but it doesn't have any practical values. Okay, signal dependent means first of all it's computationally expensive, and the main problem is this: you need to solve this encoder-decoder communications. You need to use the same set of basis functions. So somehow you have to communicate the basis function over, and that is as costly as just sending the raw signal, right? N times. So completely useless from that aspect. So how do we solve this practical? Okay, now that we learned this nice lesson, we learned a very powerful lesson. We should design a good transform is the set of eigenvectors, but in order to solve this problem, we have to assume a reasonable signal model. Okay, if we have a reasonable signal model, we can compute the RXX in advance, and it stay the same, right? We send that RXX over just one time, right? And then we're done. We establish the encoder-decoder communication, okay? And then after that, we just use that same set of basis functions. Okay, so in practice, what people did is assume a reasonable signal model, for example, the AR1 model that we played around yesterday. Okay? There, you know exactly how our x-axis look like. And you all can always compute. You can always compute the eigenvectors. Okay? And then you store it at both places. You store it at the encoder, you store it at the decoder, using the same set. Okay? So the problem is it can only work well if your signal happens to match a signal model. If your signal doesn't match a signal model, then you are suboptimal. Okay? That's the way it is. So now it turns out that a good KLT approximation for a smooth signals model is the DCT, discrete cosine transform. Okay? And hopefully today in our MATLAB demos and assignments,